So we're looking at techniques of derivatives. And so actually the first thing I want you guys to do is if you have the following function and it tells you to take the derivative, I want you to come up with what the rule is. And so one of the rules that we had come up with this week was if you have f of x, and this is equal to some constant, who can tell me what the derivative of f of x is? If you had a constant. So actually, I'm going to have you guys give me feedback. So you can just chime in if you want. Okay. So, or you can type in too. So you're right. So you're telling me it's 0. So right, the derivative of constant is 0. Okay, cool. You know that. What about if you have f of x is equal to x? What would that derivative be?
Zero.
So if we apply that rule, right? This exponent is 1, right? Actually, before we do that one, maybe give me the general power rule. So if we had f of x is equal to x to the nth power, what is the derivative of that one?
Nx to the n minus 1.
Right, so n times x to the n minus 1 power. So again, we kind of brought this power down front and then we just subtracted 1 from the exponent. So if we use that rule, let's look at this one. So some of you had it right and some of you were off on this one. And the reason I wanted to do this one is because it's one that we should know and it's not too bad. But if we bring this power down front here, that would give us 1, right? And then it's x and it says subtract 1 from this power, 1 minus 1. And so 1 minus 1 is 0. And so we have x to the 0 power. And x to the 0 power, anything raised to the 0 power other than 0 is 1. And so the derivative of just x is 1. So what if you had something where f of x was equal to c times g of x, and instead they say find df dx. How would you express that one? Where c is just a constant.
C times a derivative of g of x.
Right. And so c times the derivative of g of x. So this is just the other notation of saying we're taking the derivative of our function f of x. And so instead of saying f prime, and so how could we rewrite the derivative of g of x and the notation that we had started with here, which I think is Leibniz notation? So dg all over d of x. So technically, and someone chimed in about the product rule, and technically if we use the product rule here, we'll see that we get this. Again, if I was writing this as, another way to write it was f prime of x here, this is equal to c times g prime of x. Just different notation again. But someone had chimed in about the product rule. And so we can think of this as the product rule. We didn't here. That we can take the derivative of the first times the derivative. Actually, before I tell you the product rule, that was one of them I wanted you to see if you remembered. So if you've had a function f of x was equal to some function g of x times h of x, anyone remember what the derivative was?
Is it g of x times the derivative of h of x plus, or was it minus? Oh, dang, that's wrong first. Forgot if it was plus or minus.
Anyone remember?
The g of x, derivative of h of x
On to the
plus
false
h of
state
x, g of x of.
That's hilarious. Sorry. I love all the participation. So yeah, so f prime of x is equal to g of x times h prime of x. And then someone was saying, you're asking plus or minus, so it's plus here. But if it was, well, actually, we'll not talk about that right now. And then after the plus, it's the derivative of the other one times the original function of the one that you had taken the derivative here. So it doesn't matter order here, but it does matter when we are looking at the derivative of a quotient. So I just wanted to use that right now and kind of prove why this is true using the product rule. And so in our case here, if we said that f of x is equal to c times some g of x, using the product rule, find f prime of x. Should say g of x here. Sometimes my parentheses, they think they're ovals. And this program just automatically does shapes, which is kind of nice. I guess I could turn off. Okay, so you just told me that product rule. So if we looked at c being our first function and g of x being our second function, looking at f prime of x, we would have this is equal to c times the derivative of g prime of x plus the derivative of c, but the derivative of a constant is just
0.
0 times our g of x. And so c times g prime of x is c g prime of x, but 0 times anything is 0. And so this is equal to what we had up here. So there's just, there was a couple different rules that we could have used to derive that. So really not having to go through all that product rule, it's easier just to know that that coefficient in front, you can just pull it out and take the derivative of the other piece. Okay, so there was one other one I think we looked at. Yes, we did. F of x is equal to, let's say, g of x all over h of x. So taking the derivative of that, who wants to try?
This is when we subtract.
Yeah.
So
Subtraction.
g of x times the derivative of h of x minus derivative of g of x times h of x over, pretty sure, h of x, is it squared or something like that?
I'm sorry, I missed what you got in the numerator. Maybe I wrote that down wrong. Will you
Just
repeat
H or no? Would it just be H?
the g of x times h of x?
Yeah.
Wouldn't those be maybe h of x times g, the derivative of g of x minus the derivative of h of x times the, I'm not sure if I'm saying it correctly,
So you said the derivative of g of x all
times
times
h of x minus the derivative of h of x times g of x.
You guys agree? Not agree?
Denominator just h or no?
So it's just h, when they do the function, sometimes they don't put the x there, but this is just, this is a function of x. It is squared.
Okay.
And you don't take the derivative of the denominator in that denominator piece. You guys agree with that one? Okay, so this is where you got to be careful because order does matter. Where the product rule, it didn't. And so here, remember, you're always going to take the derivative of the numerator first. So Jason was right when he was saying take the derivative of the numerator first, times the denominator h of x, and then minus. Then we take the derivative of our denominator. And so times the numerator. And so remember how I was kind of going on yesterday about how, you know, it doesn't matter with the order when we do the product rule, but how I like to say, you know, derivative of the first times the second plus the derivative of the second times the first. Well, kind of thinking of always in that order, it's kind of the same thing with the derivative when we're using the quotient rule. It's just that the minus is here. Derivative of the first. I don't know, maybe if that helps or not. But commutative property does work for the product rule, but not for the quotient rule. Okay, so these are just helpful, and I just kind of wanted to go through them again just because we have them here, but also it's something that, you know, you want to have memorized, and if I quiz you on it and stuff, maybe, you know, it will be faster for you to memorize it if you already don't have it memorized. So those are things that you're going to want to know because you're going to be using them a lot. And then there was one more that we did not get to, and this was the last one, property that's in this chapter, and that is the derivative of e to the x. And that's not an example, it's just a rule. So the derivative of y equals e to the x is just e to the x. So we don't really have as much tools right now to prove this, and so we're just going to take it for granted for now. So let's look at a couple more examples. And so let's say you're given r. This is equal to e theta all times 1 over theta squared plus theta to the negative pi halves. And it wants us to find the derivative of the function. So basically this is r, but this is really, if you want to think of it, if it helps you better, think of it better, this is really r sub theta. So find the derivative of r sub theta. So the variable that we're taking the derivative with respect to in here is theta. So if this had been f of x, the variable is x that we're using, this is just theta. So treat theta like it's x. And so when we take the derivative, we can use our general power rule. We're gonna also need to use the product rule here because we have e sub theta times this. We could distribute if we want, but then we're gonna have to use some other rules. We'll have to use product rule again. So let's rewrite r a little bit. Let's rewrite this 1 over theta squared so that this theta is in the numerator and we can use that general power rule. And so rewriting this, we have r is equal to e theta all times, well, we can rewrite this as theta raised to the -2 power, bringing this up into the numerator, changing the sign of the exponent, plus theta negative pi halves power. Okay, so we need to use a product rule. And we just said that the derivative, so let's do always derivative of the first. So the derivative of e sub theta, we just said was itself e sub theta. So derivative of this e sub theta is itself. And then we're supposed to do times the second function, which is theta to the -2 plus theta to the negative pi halves. And then it's plus the first function, which is just e to the theta, all times the derivative of the second. So we're just using our general power rule here. So let's bring down our power down front. So this would be -2 theta, subtract 1 from our power, so -1. Same thing with the next piece, plus, so the derivative of theta to the negative pi halves power, bring our power down front. It just looks ugly. Bringing our power down front is negative pi halves theta. Take our power, which was negative pi halves, and we're going to subtract 1 from that. I'm going to write that 1 as 2/2 here. And then that is the derivative of our second function. Notice that I did not write dr d theta here or r prime. So we have to represent that this was the derivative of this. I'll just do r prime. And I'm just curious, no, they don't show me. So, I mean, we could clean it up. I mean, again, if we want to find out when this is equal to 0, we could do factoring, pull out the e sub theta. I'm not going to worry about this that much, but we find that the derivative here is e sub theta. I could rewrite this because I started with a positive exponent, no negative exponents. We could rewrite it, although this was a negative exponent, so that doesn't matter. So theta to the -2 plus theta to the negative pi halves, all plus e sub theta, -2 theta to the -3rd power, plus a negative, so minus theta, oops, I forgot my pi halves, so minus pi halves theta, and then negative pi halves minus 2 halves is negative pi minus 2/2. So putting multiple rules together. This one. Okay, so let's say you are supposed that you're given that u and v are differentiable. and they tell you differentiable functions of x, and they say that u sub 1 is equal to 2, u prime of 1, the derivative of u at 1 is equal to 0. They give you that v sub 1 is equal to 5, and the derivative of v at 1 is equal to negative 1. So given that information, you want to find the following. Find all the values of the derivative at x equals 1. So find all the values of the following derivatives. At x equals 1. So the first one they want us to find is the derivative of u times v. So notation wise, d dx uv. So this is saying that I haven't taken the derivative of our function yet. So notice that we have to use the product rule. So we're going to take the derivative of the first times the second. I'm going to write it like this. D dx of v plus the derivative, actually, and I just did it separately than what I just told you to do. Let me just rewrite it again. So take the derivative of the first. So d dx of the first u all times the second v plus the first u times the derivative d dx of the second function v. So if we look at this, I don't know why we did it this way, but this is now plugging in. Let's look at this one. This is equal to 1. So another way to write this is we're looking at what is u prime of 1. This piece here, we're looking at v sub 1 plus, looking at our original function, u sub 1 all times the derivative of v, which is v prime sub 1. Given all that information up here, we can find that without even knowing what the functions are. So u prime of 1 we have is 0 times, well, it really doesn't matter, v sub 1, which is 5, plus u sub 1, which is 2, times v prime sub 1. Which is negative 1. So 0 times anything is 0 plus 2 times negative 1, which is negative 2. And I shouldn't say 0 times anything is 0 because we've been saying that 0 times infinity doesn't make sense. And that was an indeterminate form. It's pretty much, it's just seeing if you know how to use your rules of exponents. I'm sorry, your rules of derivatives here without you having to go through a lot of the work. So you need to know that you need to use your product rule and how to plug stuff in and what that meant. One more. So if it said find d dx of 7v minus 2u. Well, this one's actually even easier. This is 7 times, because I don't have to use the product rule here. So this is 7 times the derivative of v, so v prime of x, minus 2 u prime of x. So 7 times the derivative, now we're plugging it in when x equals 1. Then we have 7 times negative 1. Oops. Minus 2 times u prime sub 1, which is 0. Or this is negative 7. Okay, so this is where I think we'll watch the one video, because I feel like, and maybe watching the video will help you understand or remember the tricks of taking the derivative, but also kind of another intuitive kind of reasoning behind what's going on when we're taking a derivative of a function. So I'm going to pause or stop this.